Hello, and welcome to a lecture on electromagnetics in two dimensions. I'm Steve Ellingson. Here's an overview of this lecture. First, why are we interested in electromagnetics in two dimensions as opposed to three dimensions? And then I'll show you the formulation of the 2D radiation equations and the associated far-field expressions. Okay, so first, why 2D? Well, many practical problems are essentially two-dimensional. For example, cylindrical reflectors. A cylindrical reflector is something that kind of looks like this. That's the paraboloidal cross-section, and then it's extruded in this direction. And then they're usually fed with some kind of line feed, which looks like this. So that is essentially a two-dimensional antenna, although it's obviously not rigorously two-dimensional. We can analyze it as a two-dimensional antenna. An example of an application of this kind of antenna is in airport radar, where you may see something like this on a pedestal and rotating at a rate of once every 12 seconds or so. Another example is sectoral horns. So a sectoral horn is a horn that kind of looks like this. Turns out that to a good approximation, you can model this as a two-dimensional horn in this dimension or a two-dimensional horn in this dimension. So in flatland, you can analyze it as a structure that looks like this and then compute its radiation pattern. And you may be able to use this as a quick way to work through some possibilities before settling on something that you would then analyze using three-dimensional techniques. Many other problems can be decomposed into one or more two-dimensional problems, which are more easily solved and then transformed back into the three-dimensional scenario. So perhaps this is an example, the sectoral horn, but what I'm really referring to is more complicated problems, such as diffraction from complex surfaces. And we'll probably say a little bit more about this when we start talking about GTD and high-frequency diffraction problems. Third, the problem is simpler to visualize in two dimensions, and often it's easier to gain insight that's useful for analysis and design. So, for example, once again, the horn problem or the cylindrical reflector antenna problem, sometimes you can get close, or at least you can gain some insight on how things are working in 2D without the additional complexity and computational effort required to do three-dimensional problems. And then two-dimensional problems are simpler and faster to compute, but this is especially an issue if a lot of iteration is required. So this is a technique that can be used to speed up that iteration if it's necessary. Okay, so electromagnetics in 2D. The drawback is that in order to realize these useful features of two-dimensional analysis, we need different expressions for the radiation equations and the far-field simplifications. Now, it's not a completely new theory. It's just that to get the benefit of two-dimensional analysis, we need to take the three-dimensional equations and apply them to the two-dimensional problem. So 2D analysis will prove useful in this course, so it's worth the trouble to do this. And to be honest, it's very little trouble. So what follows here is a crash course in the necessary theory. Two primary ideas are listed here. First, the exact formulations turn out to be Hankel functions in the distance rho. So remember, this is a two-dimensional problem. We don't have r because r is, in general, x squared plus y squared plus z squared square root. In two dimensions, we only have two Cartesian coordinates to worry about. So, for example, rho x squared plus y squared, and then we're assuming everything is constant with respect to z. Second, the far-field formulations are cylindrical waves. In 3D, we have spherical waves, at least in the far field. In 2D, we have cylindrical waves. Whereas spherical waves go as 1 over r, at least in field strength, 1 over r squared in power. What happens is cylindrical waves go as 1 over the square root of rho. And then power goes as 1 over rho. In the far field, two-dimensional waves exhibit the same phase factor that you'd expect. So you tend to see phase factors that go as e to the minus jk rho, just as you'd expect. So that part is the same. Okay, here's a solution for radiating line currents. So in any two-dimensional problem, instead of having point currents, you have line currents because the problem must be invariant with respect to one of the 3 Cartesian coordinates. So we usually select z to be the invariant coordinate. So here's a line current. With no derivation here, I will simply tell you that the magnetic vector potential goes according to this expression, mu over 4j. Here is the expression for the electric current density. There is the Hankel function I referred to. It's a Hankel function whose argument is k, the wave number, times the distance between the source and the field point. Then to get h, it's the expected relationship. There's nothing different there. And then to get e, you can just use one of Maxwell's equations, just as you might expect. We'll simplify these for the far field in a moment. For radiating magnetic currents, things look very similar. We get an electric vector potential expression, which goes as epsilon over 4j times the magnetic current. Then we get a Hankel function that goes as wave number k times that distance from the source point to the field point again. And you could also get this from duality, right? You could take the expression I just showed you for the magnetic vector potential, apply duality, and get this expression. Electric field given by the curl of the electric vector potential. Magnetic field given by Maxwell's equations. Okay, so to get the far field approximation, we need to do some preliminary work here. We have these Hankel functions, which to be honest are not pleasant to compute. They're special functions. Normally they're expressible only as series of terms, and that series is typically infinite. So we're not really interested in doing that. We're interested in getting to the far field. And it turns out that if the electrical distance into the far field is large, here we're saying 2 pi over lambda times that distance from the source point to the field point, if that's much, much greater than 1, then it turns out that the Hankel function can be approximated very, very well. This is an excellent approximation as the square root of 2j over pi times wave number times that distance. And then here's the expected phase factor. So you probably will never have to grapple with the Hankel function unless you're actually in the near field and you can't afford to make this approximation. And this is analogous to throwing away the 1 over r squared terms in the 3D representation. We can further simplify this using the far field approximations. We can replace this distance here with just rho in magnitude, because typically that distance between the source and the origin doesn't really contribute much to the magnitude. And then we can do the exact same thing we did in the 3D case to simplify the phase factor. And then, of course, it's common to separate this out. So e to the minus jk rho here, that's our cylindrical wave. And then a factor here, which is simply talking about where the source element is with respect to the origin. So far field computation. Okay, so first, I'll remind you, I showed you similar slides to what I'm about to show you back when we first talked about the three-dimensional case, the most general case, probably one of the first few lectures. And here, I'm just repeating what the exact approach is, at least once we have this approximate magnetic vector potential. If I go into the far field and I replace the Hankel function with the simpler form, then I get the simpler integral. So you'll note this integral looks very, very similar to what you have in 3 dimensions. So that's not significantly more difficult. In fact, it's about the same amount of work, same amount of complexity. We just get a different coefficient out front here. Here is your cylindrical wave, e to the minus jk rho over the square root of rho. That's the cylindrical wave. And then, again, using far field approximations that we've already discussed, you can quickly get the electric field simply by removing the radial part of the magnetic vector potential and multiplying by the right constant. And then you can use the plane wave relationship to get H, right? That's in the far field, everything is locally planar, so you can use the plane wave relationship to get H from E. For magnetic currents, again, I'm repeating the straightforward procedure for getting the fields from the electric vector potential. If we go into the far field, then a very similar thing happens. We take the Hankel function and we replace it with a simpler form. This integral is very familiar looking, very simple to deal with. This set of constants is a little bit different than what we have in 3D case, and there is a cylindrical wave. To get H in the far field, we just remove the radial component of the electric vector potential and multiply by the right constants. And then to get the electric field, we use a plane wave relationship. Or alternatively, we can go directly from the electric vector potential to the electric field. So that's all there is to it. Here's some concluding remarks. So what is a 2D problem? Let's not lose sight of what we're talking about here. It's simply a problem in which there is no variation along one of the Cartesian coordinates. That is, for example, maybe we're saying there's no variation in the problem along the z-axis. We're not necessarily saying that we're living in flatland, right? We're not necessarily coming up with some artificial thing just for the purposes of simplicity here. Some problems actually are two-dimensional in the sense that they exist in three-dimensional space, but they only vary in 2 dimensions, x and y. It's worth noting that it is entirely possible to solve 2D problems as 3D problems. There's no reason why you have to use anything I've just shown you in this lecture. But usually the reason not to do that is because it's typically a lot more work and often leads to awkward mathematics. It's often clearer and simpler to use the 2D formulations if they're appropriate. And then the key idea is also that in 2D, you end up with cylindrical waves in the far field as opposed to spherical waves. Cylindrical waves go as 1 over the square root of rho. Spherical waves go as 1 over r. And then to summarize some uses, cylindrical reflectors, sectoral horns, numerical determination of diffraction coefficients, and exploration of problems that would otherwise be too complex to do in 3 dimensions. This concludes this lecture on electromagnetics in 2 dimensions.